Now that we have a bit of understanding of what temperature is, we should look at the practical aspect of using it. In this lesson video, we're going to investigate the question, what does a thermometer actually measure? And try to understand how we can know that temperature is being measured correctly. I said before that scientists developing thermodynamics had to add a zeroth law to help define temperature, and what they came up with was this. If we have three objects, 1, 2, and 3, and they each have a measured temperature, T1, T2, and T3, if T1 equals T3 and T2 equals T3, then T1 equals T2. Simple enough. All that is saying is that temperature is a thing that can be in equilibrium, and we are going to base thermometry on that principle. We have to really, because we cannot directly measure the average kinetic energy of all the particles in a body. So, for measuring, we have our Kelvin scale, which is a bit like the thermodynamic scale, except it is more convenient because as well as absolute zero, the absolute point of minimum kinetic energy, it also has the triple point of water defined as 273.16 Kelvin. I've got a container here with water at its triple point. It has nothing inside except H2O. Its pressure is 611.66 pascals. That's 0.0060366 atmospheres. But more importantly for us, its temperature is 273.16 Kelvin. That's the definition. So let's call that T3, and so T3 equals 273.16 Kelvin. Now I have this other container labelled 1. It is the same temperature as 3, so T1 equals T3 equals 273.16 Kelvin. And in this container labelled 2, it is the same temperature as 3, so T2 equals T3 equals 273.16 Kelvin. Because of the zeroth law, I have total confidence now that T2 is the same as T1. Now that might seem all nice and obvious, but surely you have seen before that sometimes what seems obvious is not correct. So for this, we need to have total confidence, because our whole world of thermometry is going to depend on it. Let's take a blank liquid in glass thermometer and put it in this box. Its temperature will become exactly 273.16 Kelvin. The temperature will cause the thermometer to change somehow. In this case, it causes the length of the liquid column to get longer, so we can mark the length with a scale and label it. If I take the thermometer over to container 4 and put it inside, I can then measure the length of the liquid column. If it is at the marker, I know the temperature T4 is the same as temperature T3, so it is 273.16 Kelvin. That is how a thermometer works. We have a standard somewhere, and we build an instrument that we compare to that standard. We can then take that instrument anywhere in the world to measure the temperature of other objects, knowing that we are really comparing its temperature with our standard. This means we are never really measuring temperature with our thermometers. We are comparing how the object causes a change in the thermometer with how our standard caused a change in the same thermometer. This change is a change in a thermometric property, such as length, density of a liquid, volume of a gas at constant pressure, resistance of a metal, or EMF of a thermocouple. Anything that changes when temperature changes is a thermometric property, and those are the most useful ones for making working thermometers. On some levels, this will seem like a very basic lesson video, and your knowledge may not have moved along very far, but I doubt you have thought about thermometry, about the process of taking a measurement, about understanding what measurements are actually doing with such precision before. Thermometers use a thermometric property, a property that changes with changes in the kinetic energy of its particles, and the 0th law of thermodynamics to compare the temperature of the object we are measuring with a known standard. Mathematically, it is robust, and that means we can be confident to use such measurements for complex engineering constructions, for critical medical diagnoses, and for making the perfect coffee.